Morning, folks. How we doing? It's the start of week 2. I'm getting some recording done here on a Monday morning. Getting a little weird with some air. Yeah. Okay, give it a few more minutes and then we'll get started here. I love this track. Hope your weekend went well. You got your homework done. I saw a lot of you got that. Okay. I could jam out to this all day, but it's time to get it going. All right, folks. So we're getting into this chapter 2 here. And chapter 2 is all about diving in to the atom molecules and ions. We're going to really start building up the chemistry. And I'm going to start this chapter by telling you a story of a number of scientists whose discoveries all led to understanding the structure of an atom. And so the first person I want to talk about is J.J. Thomson. So let me make this a little bit thicker. So now you can see that I've got names and years and stuff. I'm not going to make you like memorize names and years and where all these people are from and what they did. This is more for your own interest. But I'll review the learning goals here momentarily. And what I do want you to understand is the structure of the atom. So J.J. Thomson gave us the famous cathode ray tube experiment. And so the way this experiment went, he had this evacuated tube. And in this tube, of course, he had a cathode and an anode. If you take Chem 110 here, like all of you will, we'll really dive into the electrochemistry and what's going on here. But you have a high voltage source, basically a battery, okay? And when you put a negative charge on the cathode and a positive charge on this anode, you're separating the charges. And what ends up happening is electrons want to flow to complete that circuit. We'll get into that in far more detail in Chem 110. But in any event, this ends up creating, effectively, it's an electron gun, is what it is, okay? So these electrons fired out of this anode here, and behind this, what you see here, this phosphorescent coating. So what that allowed J.J. Thomson to do was to view the beam of electrons. You couldn't see them. They'd be invisible to the eye. But under this phosphor screen, they light up, they glow when they hit that phosphor screen. Much like when you have, when you turn a black light on and you see like your fluorescent or your phosphorescent clothing, okay? And so what J.J. Thomson noticed when he put magnets on either side of the electron beam, he could get that electron beam to curve into the magnetic field, okay? Or similarly, when he put charged electric plates, the electron beam also traveled, was influenced by these electric plates. And he always noticed that the electron beam wanted to travel towards the positively charged plate. So this allowed him to conclude whatever particles were coming out of here had to be negatively charged because they were always attracted to the positively charged plate. Okay. And as it turns out, as we'll discover later in the semester, electrons spin, and a spinning charge, something that's got a charge and spins, ends up having a magnetic moment. So that's how these electrons, because they're also spinning round and round, that gives them magnetism, and that's why they were also influenced by this by the magnetic field of those two plates. Okay, so that's the cathode ray tube experiment, which led to the discovery of an electron. But by no means has the atom been discovered, right? Science is collaborative. Okay. So around the same time, Robert Millikan, who's an American, he's actually from Caltech. Pretty cool. So he did the famous oil drop experiment. And this experiment, I'll describe it in a moment, but basically the results of this experiment in combination with J.J. Thomson's experiment allowed us to figure out, yes, the electron is negatively charged. And so it has a charge of negative 1.602 times 10 to the minus 19 coulomb. Let's see if I can spell coulomb. I'm a terrible speller. So coulomb is a unit of charge. Okay? And he also determined with great precision the mass of the electron, 9.109 times 10 to the minus 28 grams. That's tiny, teeny, teeny, tiny. So how was Robert Millikan able to do this? Well, in this experiment, okay, he had this large chamber, and it had positively charged plate and a negatively charged plate. That's these blue plates here. He also had an atomizer. So an atomizer is also very similar to a vaporizer or a nebulizer. So you can put some liquid in it and squeeze this bulb, and it's going to sit out like push out like a cloud of particles. In this case, oil particles. Okay, and all of these oil particles or oil drops, they're not charged. It's just regular oil. Okay, and so they started falling down this tube due to the effect of gravity. Right, gravity is going to bring these things down. However, he also shot some X-rays through this, and those X-rays influenced the oil drops to become ionized. So if we have here an oil drop and it's getting fired at by an X-ray, the X-ray is energetic enough to knock out some electrons, as it turns out. It knocks out electrons out of the oil drop and left the oil drop positively charged, and even some of these oil drops were left negatively charged. Okay, so because some of the X-rays were also able to strip some of the bonds out of the molecule, so these oil drops become charged. Okay, and as a result, let's erase that because that picture is rather confusing. So basically, let's just say after the X-rays shoot the oil drops, they come out and they have this charge on them. Okay, and the ones that are positively charged are going to get attracted to the negative plate, and of course the ones that were negatively charged are going to get attracted to the positive plate. See, here's a positively charged plate right here and a negatively charged plate right there. And what's really cool about this, in the case of the negatively charged particles, right, gravity wants to make these particles fall downward. Let's see if I can change the color here for this thing. Yeah, so gravity wants these particles to fall downwards, right? I'll write force due to gravity. However, in the case of these negatively charged particles, because there's this positively charged plate here, those particles were actually attracted up. So I'm going to say force due to the charge. Okay? And so what Millikan observed in this little microscope were some particles were floating up, some particles were, of course, falling down, and some particles were perfectly balanced, right in the middle. So their mass and their charge would allow them to just float between these two charged plates. So a really, really cool experiment. And what that allowed him to determine, this charge that's on these particles can exert a certain force when put into this electric field. And that allowed him to determine what the charge and mass of the electron was in combination with J.J. Thomson's experiment. So J.J. Thomson was able to figure out what I'm going to call the mass to charge ratio. So based on how much these particles were curving and deflecting, he could figure out what the mass to charge ratio was. But in combination with Robert Millikan's experiment, they were actually able to determine both of those two numbers, which is really cool. Okay? So now we have this idea that matter contains these things called electrons. But the scientists at the time still did not know how these electrons were distributed through the atom. So then J.J. Thomson, so he was British, okay, and so he gave an analogy of plum pudding. Plum pudding is not pudding. Plum pudding is raisin bread. It's a British thing. Raisin bread. Don't ask me why. I'm not from England. But anyways, here's plum pudding. And so in Plum Pudding, you have these raisins like all distributed out through the bread, right? So J.J. Thomson thought that the atom was all this positively charged stuff. So positive charges distributed throughout a spherical atom, and all like the little raisins, if you will, were the electrons, okay? Kind of randomly spread out through the atom. Okay. As we know now, that's not correct, but it's not a bad first guess because he's basing this, off of his observations, right? We talked about the scientific method last week. So he got a set of observations and is trying to use that hypothesis-motivated science to describe what's happening, okay? So then comes along Mary Curie, okay? And with her husband Pierre and another gentleman named Henry Becquerel, they famously said, "Gentlemen, you have misunderstood the atom." Okay. And I'm not going to spend a whole lot of time talking about Mary Curie right now because in Chem 110 we're going to talk about radioactivity and radiation, and we'll get into a ton of detail. But you should totally check out this movie. I think it's on Amazon Prime. Okay, there is a brand new movie. My wife and I actually just watched this the other day. That describes Mary Curie and her life's work. So cool. I thought it was such a cool movie. You should totally watch it. So in the movie, they show famously how she was able to discover two new elements, plutonium and radium, by using this material called pitchblende or uranite. They had to go through tons and tons and tons of pitchblende. And of course, watching them do their work, makes you cringe because they're holding like these samples of polonium and radium and they had no idea just how toxic that stuff was. And they're just holding it like sleeping with it in bed, like these little glowing containers. So watch the movie about Marie Curie on Amazon Prime. It's really cool. But famously, she and her colleagues were able to show how people had completely misunderstood the structure of the atom. Okay. So then now this gets us to the famous gold foil experiment conducted by Ernest Rutherford. He's from New Zealand. Okay. And what Ernest Rutherford was able to do was take a source of radiation, a source of radioactivity that because of Marie Curie's work, we're now able to do that, to use radioactivity. So an alpha emitter is an alpha particle, okay? So we'll just say radiation, okay, in the form of an alpha particle. And he took a very thin piece of gold foil, so imagine aluminum foil, right, but made out of gold, okay? And he had another one of these screens that would allow him to see any particles or electrons. Of course, they have to strike the screen so that he can see them. They're not going to be able to see the beam like is shown in this picture, but this fluorescent screen is going to show you any particles that deflect, specifically the alpha particles, right? And so what he found was the vast majority of the particles just went straight through, okay, went straight through the foil and appeared on the other side. However, some of them came straight back. Some of them were deflected at some angle, okay, right? So these are all particles that are now being deflected. And he famously said the result was comparable to shooting a howitzer at a piece of paper and having the shell reflected back, okay? In the case of these beams that are coming like straight back. Shooting a howitzer at a piece of paper and having the shell come back. In case you don't know what a howitzer is, this is what a howitzer is. So could you imagine having like a piece of paper right there and then it like comes flying back at you? And that's the equivalent analogy. That is what happened. So what's going on here? Okay. So this is J.J. Thomson's, Plum Pudding model. Okay. And so the idea here, if there is this region of positive charge that's like spread throughout the atom, then these alpha particles should just pass straight through. Maybe occasionally when they hit an electron, they'll be deflected. But given just how tiny these electrons are. Right, Rutherford already knew how tiny they were from J.J. Thomson and Robert Millikan's work. There's no way one of those alpha particles could be deflected by an electron. Because, as we'll learn, an alpha particle contains 2 protons and 2 neutrons. So it's a helium nucleus. We'll learn that as we progress through the semester, okay? So these alpha particles are really quite giant compared to an electron. So if they hit an electron, they should just shred it to pieces. And in fact, that's exactly what happened in Robert Millikan's experiment, right? He wasn't using alpha particles, but he was using X-rays. And those X-rays were able to shred electrons and bonds out of the oil so that it left the oil charged, okay? So now this is what allowed Rutherford, he was able to refine the hypothesis of the structure of the atom. And this was the result. This was the conclusion he came up with. That there had to be some extremely dense, so this says concentrated. I'm going to write extremely dense region of positive charge and mass at the center of the atom. Everything else, this blue area, this is called a diffuse electron cloud. We now know that that is like virtually nothing. There's basically vacuum in this diffuse electron cloud. And of course, occasionally electrons spread around. So that idea of J.J. Thomson's Plum Pudding model was somewhat correct, that these electrons are spread around. But the material between the electrons and this dense material at the core that we call the nucleus, it was kind of unexpected that this area was largely nothing, and that this nucleus is extremely dense, dense enough that you could fire an alpha particle at it and it would fire right back, okay? And when I say extremely dense, I'll give you just an approximate density. So remember, density of water, we talked about densities last week, and you'll continue to talk about density in your lab, okay? So the density of the nucleus, if you could take a bunch of protons and neutrons and distill them down, okay, it's about 10 to the positive 15 grams per milliliter, or grams per cubic centimeter. 10 to the 15, that's like the mass of a mountain distilled down to like 1 cubic centimeter. That's crazy, okay?